Next, we need to apply the Lagrange equation of motion to simple pendulum. To obtain the equation of motion of simple pendulum by using Lagrangian method and hence deduce the formula for its time period for small amplitude oscillations. So this is our simple pendulum. Length of this pendulum is L. Suppose if you do some oscillations, it's going to be oscillate like this. Okay, angle is theta. So let the theta be the angle or displacement of simple pendulum from equilibrium position. L is the effective length of the pendulum, and m, small m, small m with the mass of the bob. This is the bob. So this is our displacement from its equilibrium position. So displacement I'm going to write like this. So this one is O, this O, for more clear. Yeah, this is O, this is the point A. So distance is yes. Okay. Here OA represented the displacement S is given by S equal to L into theta. So because theta we know, right, arc by radius, from this formula we'll get this one. Okay, S divided by L. So therefore S equal to L theta. This is the simple derivation. So we know the kinetic energy of the system T equal to 1 divided by 2m x, sorry, v square. Okay, so here velocity of system we can write ds divided by dt, right, rate of change of displacement. Therefore here S I know, S value L into theta into dt. Here length of the pendulum is constant L, then we can write this one is theta dot. So therefore I'm going to write kinetic energy of our system 1 divided by 2 m L square theta dot square. Okay, this is our kinetic energy term. Let us look at this potential energy term. For more clarity, I'm going to draw this one like this pendulum. This is our pendulum. This one is so okay. This one is enough. This much distance. after displacement, this is the distance. Okay, so this is the uh, length of the pendulum. So angle theta, this one. So therefore we know this axis value right now. This is L sine theta, right? What about this one? L cos theta. So this is the L1 minus cos theta, right? L minus 1 minus cos theta. Okay. Now if you look at more clarity here, so this is what I tried to explain here. This one, this is the dot. This is L sine theta. This portion is L into 1 minus cos theta. This is L cos theta. Okay. So this is the extended diagram. So now I'm going to write the potential energy term. Okay. So if the potential energy of the system when Bob is at 0 is 0, then the potential energy when the Bob is at A is given by this equation. So this is the our system, right? So we want to find potential energy of the system at point V equal to mg. It's better to give this point is B. Okay. Okay. OB. Then this OB I'm going to write like this mg OC. So if you give here the C OC minus B, just put the values. Length of the pendulum we know. Length of the pendulum OC L. What is BC value? L cos theta. Okay. mg, this is L minus L cos theta. This is the explanation, complete explanation. Okay. So if you want more clarity, so you can write here itself BCL equal to sin theta, sorry, cos theta. Yes, wait. Cos theta. Then BC equal to L cos theta, right? Okay. Now I know potential energy of system and kinetic energy of the system. Both values I know. Then we need to write first Lagrangian. Then we need to apply the Lagrangian equation of motion. So what is our Lagrangian equation here? Lagrangian, not Lagrangian equation, Lagrangian L equal to T minus V. This is our Lagrangian. Then I am going to try to apply this Lagrangian. What is T value? 1 divided by 2 m L square theta dot square. We already discussed how many degree of freedom needed. Sorry, how many generalized coordinates uh, needed to describe this motion of simple pendulum. That is only one coordinate theta dot, I mean theta, right? So because L is constant, so here only one variable is theta, which is why our equation variable is theta here. Okay, minus mg L is constant, 1 minus cos theta. This is our Lagrange here. Okay, so now derive first with respect to dou by dou theta dot second term is going to 0. First term will be the m 2 gets cancelled, L square theta dot. Okay. Second term, dou L divided by dou theta only. I'm going to derive entire this equation. First term is going to 0. This one is minus uh, mgl 10 cos theta sin theta, right? Minus sin theta. This is going to plus. Therefore, mgl sin theta. This is our information. Then write down the Lagrange equation, dou by dou t, dou L divided by dou x, right? Now dou theta dot. Our degree of coordinate, generalized coordinate is theta dot minus dou by dou L partial derivative of theta equal to 0. So please substitute these values here. D by dt. What is this one? M L square theta dot minus into minus plus mgl sin theta equal to 0. So therefore ml square theta double dot, because here d by dt is there, mgl sin theta equal to 0. So this is our equation of motion. Here the generalized coordinate is theta. Okay. Suppose our system, simple pendulum having very small uh, oscillations, which means small amplitude oscillations, then we consider sine theta. This function is going to be very small, so we can write sine theta approximately equal to theta. Then we get ml square theta double dot plus mgl theta equal to 0. Then theta double dot plus g divided by l theta equal to 0. This is our equation of motion of simple pendulum by using Lagrange. So this represented a simple pendulum of harmonic oscillator of time period is given by word node. Time period t equal to 2 by root L divided by z. So this is our simple pendulum equation.